One of the most extensively used and rapidly developing equipment in gas absorption are packed towers. A packed tower is essentially a piece of pipe set on its end and filled with inert material or tower packing. It operates in counter-current flow, where the liquid enters the system through the top and wets the surfaces of the packing, and the gas stream, mixed with the effluent, enters the bottom. Upon contact of the liquid and gas streams, the components of the effluent can be absorbed into the liquid. One of the many factors which contribute to the general capability of the packed tower design is the packing material used. The primary purpose of the packing material is to provide a large surface area for mass transfer. Packings are usually made of plastic, such as polyethylene, polypropylene, or polyvinyl chloride, but can be made of ceramic or metal. They are generally divided into three classes, as follows. Number 1, random or dumped packings. Random or dumped packings have a specific geometry and are randomly packed into the column shell. Table 14-13 of Perry's Chemical Engineer's Handbook, 7th edition, provides the characteristics of different random packings. From left to right, we have the Raschig ring, the Paul ring, and the Burl saddle. The second type of packing material is the structured or systematically arranged packings. These consist of crimped layers of corrugated sheets or wire mesh that are stacked in the column. Table 14-14 of Perry's Chemical Engineer's Handbook, 7th edition, provides the characteristics of different structured packings. Lastly, grids are also systematically arranged packings that use an open lattice structure. It is also important to consider the type of packing material that will be chosen for a specific process. Some considerations follow. Number 1, cost. Plastic packings are generally cheaper than metal, and metal packings are cheaper than ceramic. Number 2, low pressure drop. Pressure drop is a function of the volume of void space in a tower when filled with packing. And generally, the larger the packing size, the smaller the pressure drop. Number 3, corrosion resistance. Ceramic or porcelain packing is commonly used in a very corrosive atmosphere. Number 4, structural strength. Packing must be strong enough to withstand normal loads during installation, service, physical handling, and thermal fluctuations. Ceramic packing is subject to cracking under sudden temperature changes. Number 5, weight. Heavier packing may require additional support materials or heavier tower construction. Plastics are much lighter than either ceramic or metal packings. And lastly, design flexibility. The efficiency of a scrubber changes as the liquid and gas flow rates are varied. Packing material must be able to handle the process changes without substantially affecting the removal efficiency. The objective of packings is to maximize efficiency for a given capacity at an economic cost. This objective is achieved through the following guidelines in design. Number 1, the vapor-liquid contact area should be maximized by decreasing the random packing size so that efficiency of packing is increased. Number 2, the surface area must be spread uniformly to improve vapor-liquid contact and increase efficiency. Number 3, the resistance to gas upflow must be minimized by maximizing the void space per unit column volume. The capacity increases as the random packing size is increased. Since the first objective aims to minimize the packing size, the ideal size of packing is such that the efficiency and capacity are both maximized. A large void volume will also minimize pressure drop of the system. Number 4, friction must be minimized by choosing a geometry of packing with good aerodynamic characteristics. And lastly, number 5, The cost must be minimized by increasing the packing size for random packings or increasing the space between layers for structured packings.